Hi there, it's Matt Venn doing another interview for the Zero to ASIC channel. Joining me today is Lakshmi, and we're going to talk about their PLL design that they've put on the Google Efabless ASIC shuttle. So Lakshmi, very nice to meet you. Thanks for coming on this interview. Maybe you can tell us a little bit about your background and how you got involved.
Yeah, I did my bachelor's in India at Amrita University. Then I'm studying my master's at Georgia Tech. So yeah,
So,
first year of my master's.
okay, and this is, did you say that this is your first major project?
Yeah, this is my first major project in BLL. I mean, like in the analog side. So like.
Okay, are you involved with Kunal Ghosh at all? Because he said he was excited to hear this video.
Yeah, I was working as an intern under Kunal, and it was under his internship that in his internship, I was working in PLL, and then I got this opportunity to work with the Efabless and go it for the tape out.
Cool. Okay, and what's your experience been like so far using the tools?
Yeah, as I was a beginner, it was from the beginning that I learned each and every tool, and then I started to learn how I could implement the design that I wanted to make. So it was really exciting. I could understand, I could learn, explore lots of things in the due process. So it was really good.
Have you used other tools, like paid for tools like Cadence or these other kind of big brand name tools?
No, I haven't used.
Okay, I was going to ask you to compare them, but obviously we can't do that.
Yeah.
So let's get on to, so I put a link up on Twitter to see if people were interested in asking questions. We've got quite a lot of questions. So I'll start off with a good one from Niklas. If you were to do a different design of a similar complexity, how much time would you need? Would you be able to do a quicker job now, do you think?
Yeah, I would be able to do a quicker job. For this, I took around 2 months of time along with my college projects and mini projects. So, if it is something of this sort, I would be able to do it at a quite faster pace because I had redone many times. Because when you design it for the first time, you won't be able to do it perfectly. So, I got a lots of exposure in this. So, now I'd be able to do it in a better.
Cool. And the other part of that question was, what was the most time-consuming step?
Um, I won't say yeah, the most time consuming part was there is one loop filter which was which I had to change the R and C values, the resistance and capacitance values. To get that correct proportion was I had to do it manually. Like we had to do lots of trial and error to get to a correct proportion. So that was the time consuming part. And there is in the charge pump, I had to change the size of the transistor. So to get a correct proportion of all these three, like the correct ratio of the resistance, capacitance, and the size of the transistor was bit
So
tiring one.
you like draw out a layout, do the extraction, then simulate it, then get the result, and then realize if you need to change something.
Yeah, I wrote the code in the ngspice. Then I did the pre-layout simulation there. Then I did the layout in the Magic. Then I got the post-layout simulation. Then I compared so that I could do a better job, like to understand if the simulation is proper to or expected as that of the pre-layout.
Okay. And what was the most frustrating?
Not like the same thing, the tiring part where I had to do the like many a time I used to fail. I mean the results which I used to get was really off. Like it wasn't expected and suddenly it comes. That was some. I mean, it was tiring. I won't say it as frustrating.
How
It was
long
a good learning process where I
for
could
each of
understand.
these cycles where you're like doing the layout, the simulation, and then comparing back to the original simulation? How long was that cycle taking you?
That was like many a time when you fix a size of the transistor, the R and the C won't be coming at that time. So it actually took me, that was the most, might be like 1 month I was working only on that ratio to get a correct value of that. So
Took a long
might
time.
be because I'm a beginner, I took that much time. That
Yeah,
could also
yeah.
be a reason.
What was, this is the last part of the question, was what was the most fun? I think that's a good question.
Like the fun, like the happiness that we get when we see the correct output each and every time, that was really exciting. That was the one which was making me work more and more.
Right, when you finally got the good result.
Yeah.
Okay, and then the another question from Niklas was, do you think the tools are ready for practical mixed signal applications? Maybe you're not the best place to answer that if this is your first time with
There were some violations, but I think like Caravel is still working on it, so I think it would be proper. Like it would be
when you say
fine for.
violations, you mean DRC violations?
Okay, DRC violations.
You said there were still some violations. I was just asking for clarification on what.
Oh no, I meant like the Caravel was having some issues with their wrapper, so they were still fixing some things. That is what I meant. But now I guess it's
The
usable. Might not be
integration.
at their best stage. They are still in their processing speed. So I think everyone can implement their project in there.
So just for clarification, so for people that didn't make a submission, we made our designs and then they went inside a wrapper that's called Caravel, and there were some DRC errors with the Caravel wrapper. So even if you get a completely clean DRC project, once you put it inside and you rerun DRC, you'll still get errors. Yeah. And we were, what was it at the end? There was like a magic number, like 140 errors you were meant to get at the end or something like that. So they're still working on that, and that's just part of the process of actually sending the files to the factory. Okay, so now I've got a question from Pepijn. This is like regarding your PLL design. How would you change it if it needed X% more Y, where Y is one of the requirements of the system? So the reason he's asking this question is to give insight into the design decisions and the transistor scaling. That makes sense?
Yeah, it was for the increasing the frequency, right? Like the output frequency.
Yeah, well, like, yeah, I guess so. If you want to make a change to your design, how would you know like which part of your design to change?
Okay, that would be like basically the main thing, which is I would say a process in a process way. Like first, the charge pump has to be in a, like the capacitance should be such that it's able to store a certain amount of energy in it, and this is the one which is providing the voltage to the VCO, like voltage control. So it needs a certain amount of voltage for the frequency to increase. So charge pump has to increase, then the VCO naturally increases, and then naturally the frequency would increase. And there is one more way we can increase the frequency, would be like changing the FD, which is the frequency divider. So when we do that, naturally the frequency would increase. I think these two would work for increasing the frequency.
So Lakshmi, maybe you can, for those of us, including me, who don't really understand how PLL works, maybe you can just talk us through the functional block diagram that we've got here.
Yeah, like we would be sending a frequency, and it would be first passing through the phase detector, and then it would be aligning the frequency with respect to the reference frequency. Then according to the result, like the up or the down signal that we get from the frequency divider, we would be passing it to the low pass filter, and we would be manipulating it again and then sending it to the actually I have a charge pump also in between these two, and from low pass filter it would be going to the charge pump, and it would be charging it in such a way that it's able to provide a sufficient value of voltage to the VCU, and then that would be the output. And then to get a better stability, we would be passing it through a frequency divider, and then that would be the reference to the reference frequency. So that's how basic PLL works.
Okay, thanks for that.
Yeah, this is the FD design. Like I had marked like this is the frequency in, and
just for clarity, FD is frequency divider.
yeah, frequency divider design. So
okay, you've got like a latch there. So
yeah, this is like I wanted to make something which could store like here in this case, like if the clock is 0, like this won't be working, so it would get stored here. Then at the next clock it would be going out, so it would be able to store the value. So I made this as a flip flop, and this would be a good frequency divider so that can store and send it at the next phase. So
does
when
that
we
divide the frequency by 4 because you've got 2 latches?
would be, no, this is a basic design which we would be implementing it for different frequencies. uh, this is something which I had I had taken from the paper. So I had made the code in such a way that it would work for 8. This is basic for basically understanding how it is I had put it. And when it comes to layout, it would be like this. Like you have the transistors coming here, then it would be going, then the same thing being repeated, and then third thing, and this is how the frequency diode layout would be. So explaining about it, like this is the inverter clock, like Fin would be coming here, then the inverter for the clock would be this, and then these are the inverters that we saw there, like here, these inverters. So these 3 are those, and then these are the transmission gates, these to be coming here, and again the inverter, and it would be coming. So that is how the schematic got translated to this.
Okay.
And then similarly the phase PFT, where this would be the circuit, and the up and the down, these like might be like yeah yeah, these are the ones which would be driving the clock. So the whole of these would be,
what's the PFD?
it's the phase frequency detector, where you would be detecting if it is an up frequency or the low frequency, up or the low, and according to which we would be giving it to the next, like charge pump and a VCO, so that we would be able to manipulate the like the two signals that we get, and we would be able to get a proper output. Like the frequency should get according to the input that we receive. So that is the function of the PFD. So the layout of it would be like this. And when to explain that with respect to the schematic, it would be like the P3 would be here, P4, and the clock 2 would be coming here, and this is the reference clock according to which the clock 2 would be judged. So, and we would be getting it as an output, like if it is an up or the down. Up would indicate that it's going front, and down would indicate that the with respect to the frequency it's at a back of phase. So that is the output that we get from it. And charge pump is basically for giving, like we won't be getting a sufficient amount of charge from the output of the low pass filter won't be sufficient enough to give a voltage to the VCU. So this would be the one which would be giving the sufficient amount of voltage. According to, if we want to increase the frequency, we would be increasing the charge pump capacitance, the parameters of it. And if you want to reduce it, this would be the one which could be used for reducing the voltage, which we provide to the VCU. So by doing that, we would be able to give a sufficient amount of voltage. Voltage is the one which would be provided by the charge pump.
Okay.
Yeah. So this was basically implemented like this in the charge pump. Like we have a enable charge pump, and then these are the down and the up signals that we get, that would be given to the charge pump, and we get an output which would be then sent to the VCO, which is the voltage control.
And this is a digital oscillator, so the output that we're getting there is a square wave. Is that correct?
Yeah, not actually a digital one. Like it would be similar to that of the input, like the similar wave similar to that of the input would be got as an output.
Okay, but it's not like a triangle wave or a sine wave. It's a square wave.
Yeah, square wave.
Okay. So you a changing voltage in is going to increase or decrease the frequency coming out.
Yeah.
Okay.
Because it's voltage controlled. Yeah. According to the voltage, it would be like manipulating the output that we get.
Okay.
So I had used ring oscillator for it. Like it's a 3-stage ring oscillator, and at last I had kept a buffer so that I could uh, the the power that I was getting as an output wasn't enough to drive the next one, like the FT which I was getting. So I had to keep a buffer for that to increase it, and that's how an extra buffer came into this place. And yeah, and an extra inverter was done because I did not want the output which is got out of the ring oscillator to get when I was keeping it without an inverter, I was getting some distorted signals. So when an inverter was kept and then another inverter was kept, I was able to get a proper wave without any distortion, like as I had expected. So an inverter was also added to that. Yeah. And this is the integrated, after integrating all the components, this is
Okay,
how
so
it
this is
looks.
everything all added together. And this is
Yeah.
because I don't know if you saw, but I interviewed Diego Hernando last week, and he said that you had put your design in with their shuttle application. So this design was also part of his application, was it?
Yeah.
Cool.
Like Muhammad had actually suggested us to keep it in a single thing because there were lots of space left in his.
Yeah, there was
And
loads, wasn't there? Yeah. Yeah, good idea.
yeah. So yeah. And this is how it comes out after avoiding it in the Caravel. Like, and might be like in the design and my repo the area is less because I wanted the PLL to be in a to confine it in a small space, and here I had lots of space left, so I did not want to take any risk, so I added lots of spaces and I had kept it at a proper place.
You added what, sorry?
Like in my repo the space taken by the whole of the PLL was much lesser than the one which I used for Caravel. That
Okay.
was because like in Caravel I had lots of space and space was not a constraint for it, so I had actually made it in a higher space, like the space I had made it more spacious.
Okay, you spread it out a little bit.
Yeah.
Okay. Cool.
And this is the view from the wrapper, like the user project wrapper. And
Right, it's really small then, isn't it?
yeah.
Probably it's maybe a bit difficult for people that aren't used to seeing the wrapper, but these vertical bars on the left is part of the power distribution grid,
Yeah, this.
and they're very small. How wide would you say your block is in total in microns?
I did not calculate it. Yeah,
Maybe like
I'm not sure.
20 microns or something like that. Yeah, certainly very small then. Okay, great. So that gives us a good overview of your design and how you put it together. Let's get on to another few questions from the Twitter audience. Brady says, why go with an integrated loop filter? Most PLL ASICs have these passives external.
Okay, yeah, that is because like it's true that we usually keep it outside. The reason behind that is because of the spacing issues we face when we keep a PLL. But there are lots of disadvantages to it. Like when we keep it outside, the noise that we have that we get that is really high. But when we keep it inside, the noise gets reduced, and the pins which are required when we keep it outside is also more. So as my PLL in total was really less, and the loop filter, I could design a smaller loop filter. So I thought of keeping it inside itself, like rather than keeping it outside.
Okay. A few questions from Tom. He says he looked in the GitHub and it's really nice, but he didn't see schematics for the design. Are the schematics available?
No, actually, I did not go. Yeah, I did not start it off with the schematics. I started off with directly writing the code in the ngspice, and then
Okay.
then the layout was made, and yeah, that was how I worked. So I did not
Okay.
design any schematics.
Will you add the schematics later, or they just you'll only link to the, because the PowerPoint that you showed earlier had links to
Yeah,
the.
that is from the reference papers that I had kept in below. Like
Okay.
those were the schematics.
Another question from Tom: did you test the process corners?
Um, Not actually all the corners. Like the present one, I had tested it only for the room temperature, and
Okay.
we can actually do it. Like I would have to change the temperature in the code. Like there is one option in that. Like when I manipulate the code in such a way that it can be tested for different corners, so that can be done. But I have not done it till now.
Okay. And the final question from Tom was: did you have any convergence issues in ngspice?
Uh, no, I did not face any. Like while I was working, I had faced some conversion issues, and mainly it was because of the errors in the code that I had written. Other than that, I did not face any convergence issues.
I don't understand that question. Maybe you can explain what a convergence issue is.
Like when you simulate it, like when the ngspice is simulated, we would be getting some errors. That is the convergence issues.
Okay.
So,
So basically, when ngspice doesn't finish.
yeah, when it is having some errors, like when the design is having some errors.
Yeah, usually I get that when I've forgotten to connect two nodes in ngspice and the circuit isn't complete, and then it says it's.
Yeah, because when when we create some errors in the naming of some elements, pins, such as yeah.
Okay, and final question from Stephen. You have a post-silicon testing plan. Do you have access to a VNA or an SSA? I don't know what an SSA is.
Yeah, I mean, my plan for like testing would be, my plan was like basically, uh, I was trying to check the output. Like I would first want to check the output if it is similar to that of the post layout simulation that I had got, and then I would want to check it in the VCO mode and the normal mode, so that I would get to know if we can directly give the IP like input to the VCO. These were the plans of my testing. Others I haven't checked on.
Great. Yeah, I think we've got like a really mixed audience. There's people who are interested and have never done it before, and they're interested because it's something new and exciting. But we've also got an audience of people with a lot of experience in the industry, and they're interested in the fact that it's open source, free tooling, and they're asking lots of technical, complicated questions. Because we also got one last week on Diego's op-amp, like someone asking if they're going to use like a machine that can do on-die testing and profiling of their design. But the machine, I had a look at the data sheet they posted on Twitter, and it looked like it's at least $1 million worth of gear. So for most of us, it's not really not really a possibility. Is there anything else you want to say, or any projects that you're working on that you want to tell people about?
Like, I'm currently working in my like I was working on a deep learning project when my back in my college, back in my university. So yeah, that is what I'm currently working on.
Cool. Well, good luck with the rest of your course. I hope it goes really well. I'm interested to hear how your PLL performs. Maybe we can do a follow-up interview when we get the silicon back.
Yeah.
So thanks very much, Lakshmi, for your time, and I'll see you all next time. Bye-bye.